Thank you. This is a new course we're putting into the APAN program. First time it's running is this summer, and then it's going to go in the fall as well. The point of the course, so a lot of our students have a growing interest in artificial intelligence, as does the market that they're applying into. And some of the needs, or some of the questions that they ask, or some of the curiosities they have, will really benefit from having a better understanding of the mathematical tools that are used in studying or developing or working with artificial intelligence algorithms. And so the point of this course is to give them that mathematical toolkit. Let me actually go, I'm just going to skip that one for a second. So the course is structured a few weeks on certain segments of mathematics that feature prominently when you're working with artificial intelligence algorithms. The students are introduced to these also. So we actually give them 2 weeks at the beginning, and then on the third week we start introducing Python code as well, which really helps them sort of take the concepts that they've been working with and see how it gets applied and sort of things that they can run on their own computer and how things are being run up in algorithms out there today. So maybe I'll go through this part a little bit. So there's a bunch of mathematical topics they learn, and they're like objects within each topic, and the point is to give them a toolkit so that when they're working on problems or reading about something, they'll have seen a lot of the objects and know what their uses are for within the discipline, how to use them themselves, and how other people are using them. So we start actually, there was also a learning objective here where we also want to encourage, there is this one point where we don't, and this might be a minor point in the larger presentation, but we don't want them to sort of take math and sort of just think of it in isolation. So we do have a responsible AI component to this course as well. This does fit in on 3 touch points throughout the course. I've sort of baked a lot into some of these bullet points. In the first bullet point, when I'm talking about the historical and social context that numbers arise in, they actually come into the course, and in the first day we're talking about the history of numbers. Actually, I'd like to say prehistory, because the history of numbers predates written history itself. There's a fun reading we do where an archaeologist is showing largely bones and cave drawings with tally marks and distinguishing how can you tell some tally marks are referring to numbers as opposed to being a decoration. And it is speculative because there's no writing to confirm it. It's a fun reading. There's obviously a lot of sort of governmental applications, which is when what we think of as maybe mathematics today starts to really grow into its own. Even from Sumer, before they had first writing, they had numbers before they had letters, and they were keeping tracks of granaries and things like that. Sorry, the course is not a history of math, but anyway, but the point of me introducing that was just that there's a human component to it, there's a cross-cultural component to it. And I just want to make sure that that's not left out before we sort of dive into all the tools and the fun things that the students learn. Then actually in that first lecture, we talk about sort of what are numbers, starting from a ground level. And after we talk about, well, what is a number, then we kind of get into what I would call the more toolkit things that people are sort of, oh, I have this problem, okay, let me take this out. Linear algebra, so it's kind of natural that in applied analytics, and a lot of, whenever anyone's doing data analysis, they're working with large, you could even think of spreadsheets, databases of numbers, and these get grappled with in a mathematical context in terms of data matrices. And then there are things that people do with these data matrices. If a common practice is principal component analysis, I think a lot of people have seen, and that actually, where does that come from? Well, that comes out of, you have a matrix, you do something called spectral decomposition, which is a way of analyzing the numbers in the matrix and how they relate to each other, and you get this very common technique for how people analyze their data sets. Then we go on to 3 weeks of calculus related to how people, when they have a problem and say a cost function or some like reward that they're trying to maximize, how do they go about maximizing that? And usually they dip into this pool of tools relating to derivatives and gradient descent, and so that's the next part. The probability and statistics now, I mean, as an analytics program, we have a lot of that sort of spread throughout the program. So what's focused on here is more the mathematical derivation from sort of first principles thinking. So like, yes, these distributions, the students probably are familiar or, I guess, with them already, but how are they derived from more base principles? We go into that with them as well. And then later on, there's graph theory, which is very fun because there's many different ways for students to use graphs. So in class, one example we use is showing that graphs can show the relationships between different sort of rows of data in a data set. And so we actually look at a famous data set of flower types, and there's 3 specific subspecies of this flower represented in the data. And it can be sort of difficult to just read the spreadsheet and understand what are the different species, but actually when you plot them as a graph where the similarities between the rows of data are actually mapped onto a graph, you will see that the subspecies actually separate out into one subpopulation, another subpopulation, another subpopulation. Whereas then they go to their homework and they see another application of graphs where actually it's a small social network, and they're talking about friends and friends of friends and who's most popular in the group and who's least popular, but the least popular actually has friends, like a wider friend of friend group, because every connection between people is modeled using the graph theory as well. So they're getting a lot of fun applications as they go along the way. Then we go into problem solving and algorithms. So one part of that is just algorithmic analysis, where if they set up their programs in a correct way, something could take 1,000,000 years to compute, or it could take 10 seconds to compute, and just being able to guess which of those 2 categories your program fits into is useful for them to be able to understand. And then another lecture is on if you have a set goal and you have a program that can try to reach that goal but doesn't know how to get there, there's different strategies that can be that your program can follow in order to solve its problems in an automated fashion, and what kind of solutions does it come with? Are they good solutions? Are they long, short? Things like that. And then the last thing here, computational theory and automata. So I really like this. There's also like one lecture after this I'll talk about, but so this has to do with what types of programs can accomplish what types of tasks. And actually part of this starts to get, and then the last lecture is all about this when you talk about the limitations of mathematics. So in computational theory, you learn about how some problems can't be solved by some types of computer architectures, but might be solved by a more improved type of computer architecture. So so leave that there, because on the last lecture, there's a few points touched on that, and the last lecture is titled just Limitations of Mathematics. One of the points, again, bookends sort of the social stuff that we were talking about at the beginning, where we talk a bit about, we have a reading on sort of the philosophical debates that have gone on between saying, okay, you have this great toolkit of math objects to play with, but don't run away with it. You can't sort of make ethical decisions out of just your math stuff. You need sort of an outside component into that. And then the other sort of 2 points touched on in that last lecture are that this idea that limitation, like in the computational theory lecture, there's like, okay, one machine is less powerful than another machine. But then there's actually several theorems about even if you had sort of the best computer available that knew all the algorithms you could ever point into it, there's still important limitations about what a computer can actually accomplish. So some of the results in that case are what's called Gödel's incompleteness theorems, which make statements. They're technical, and get me after we can go into nuances, but about how there are statements that can be true, but you can't prove that they're true within the system that they exist. Another related problem is called the halting problem, which is that you might write a program, but and this program, you may have checked the logic perfectly, but it will never, you don't know if the computer will ever give you an answer. It may run forever without actually telling you that something is one way or the other. And then, oh, okay, and yeah. And then the last one was that even in the context of AI algorithms, there are these things called the no free lunch theorems, which are that that explain that there are limitations to how well using, say, a machine learning algorithm can be at solving a problem without sort of more human input and crafting and understanding being encoded into the objects. So anyway, that's the survey of the course. I'm happy to talk about more, but that's it. Thank you.